I'll give you another example. And again, this harks back to my theme of applying the methods of the course outside the context it was taken in. I was hanging out the washing the other day, and I was halfway through hanging it up, or a third of the way through hanging it up, and it started to rain. And so there was me and my wife grabbing the stuff in before all the stuff got wet. And she said to me, "You know what you've done, don't you? You've taken your clothes. These are your underpants here on this line. You've put your stuff out to dry preferentially." And I said, "I have not." And she said, "Yes, you have, because look how many of your underpants are on this line. There's hardly any of the rest of the family's clothes here."
So you did your laundry preferentially?
Yeah, she says that because I'd only hung the first few items out on the line when it started to rain. And she said it hadn't, and I said it had. No. She said that I was being biased towards my own items.
And since you're a man, you were wrong.
Yes. But this isn't a marriage guidance counselling session by any means, and I'm by no means encouraging you to do this with your spouse. But I thought to myself, what's the null? What is the null?
The null was that she was right in saying that you...
No.
No.
No, the null is that it's random.
It's random.
And sometimes there's going to be more of my stuff on the line and sometimes less, just because of random variability. So let's just draw up a table here. My stuff, rest of family. Online, still in basket. I want to make it clear to you that even though once you've seen that it's a hypergeometric distribution, once you've seen this, it's kind of straightforward. But the hard bit is translating from the observation to the 2x2 contingency table. So let's just say that I'd done about a third of it. So I'd done, let's say, 9 items, and there was, let's say, 19 left in the basket. So that totals 28 altogether. Of which, let's say, 6 were mine. On the line, 6 were mine and 3 were not mine. And let's just say my stuff is my stuff is 13 and 15. Okay. Let me just go through that again. Let me just go through this whole process again. So there's 9 items on the line, there's 19 still in the basket. I've got 13 items altogether, and there's 15 for the rest of the family. So we've got a total of 28, either by rowing the columns or not. So the things on the line, my wife's observation was 6 out of them, out of the 9, were my things, and only 3 were the rest of the family. And 3, yeah? So what's this number here? That's going to be 12, isn't it? And that's going to be 7. All right? So again, we can calculate, using the hypergeometric distribution, we can calculate the probability of seeing this data set. So let's just try that. So white equals this, black equals that, drawn, not drawn. Okay? So white equals my stuff. I say it's rare that my underpants count as a success, I can assure you of that. How many of my stuff were there? 13. Rest of the family is 15. Drawn was 9, not drawn was 19. And my observation equals 6. So let's have a look at that.
So you can go MN KX again.
Yeah, we need the whole thing. D hyper. 6. Next one's M. Oh God, which way around is it? Number of white balls in the urn is number of my underpants, which was 6, was it? No.
Yeah.
13.
13.
13 hours later.
Yeah. And the next one was N, which is the number of black balls, which is the rest of the family. And then the number of items on the drawn is 9. There it is. Now, the p-value is the probability of scrubbed. Oh, it's still here. The probability, if the null is true, of seeing the data or an observation more extreme. Now I can't. Now we could have more extreme because it could have been all my stuff. It could have been a row of 9 underpants on the line. Then she might have had a case. Okay. However, I can say straight away that it's not significant because the probability of this data set here is 11% plus more extreme, which would exist in this case because it includes at least 9, 0. So the probability, the p-value, probability if the null is true of seeing the observational one more extreme, is not significant because it's at least 11%. All right? So I have objective evidence that I was right. Because if the null hypothesis of random drawing is true, you get a result like that 11% of the time, which is above the 5% cutoff. Do you find that convincing? She didn't. She said, there's more, there's 6, and that's it. What am I supposed to do? Say, well actually the hypergeometric distribution, I don't think that would help. Sometimes statistics can't help you with...
Statistics don't help in relationships.
No, that's right. Indeed. Of course, I'm just indexing with this 6 here, but what I can do is probability of 7 items. You see it's smaller.
Wow.
You see it's smaller now?
So
Because as I'm drawing my underpants out, there's fewer of my underpants left in the bag.
So if you had 7 on the line versus the 9,
Yes?
then it would be actually a true not
We don't know because there's 8 and 9 as well to add.
right.
Yeah? Because it's the probability if the null is true of the observation, which would be 7,
Yeah.
or more extreme. So I've got to add 8 and 9.
Okay.
Let's try that. Getting rarer now, isn't it? What's this going to show? We've only got 9. We've only got 9 draws. I've only taken 9 things out. So it can't possibly be 10. Sweet. So to work out the p-value for my original observation, okay, well let me just do it. I'll just show you how it works. Not significant, because it's above the 5% cutoff. Any system where you've got 2 ways of classifying things, you can apply this course. Go on.
7. Oh, it's the 6.
Just one more. So say from 7, if you do from 7 to 9,
If
it'll
you
be
did
less
7
than
to 9,
5%.
yeah.
Oh, well, let's try. Yes, let's try.
I mean, 6 wasn't.
So I'm 1 pair of underpants away from being significant. Thrown out. I was only doing the washing anyway. So that there's a whole bunch of examples like that. And I'll show you easier ways to do it in the next 10 minutes. I always like male and female because that's a nice way of black balls and white balls. But you can have things like left-handed and right-handed. All right? So it might be something like this: 10, 20, 30 and 60. It's 2 ways of classifying things. A 2x2 contingency table. This is a 2x2 table of counts. Okay, we can analyze it using exactly the same methodology, which is this one here. So in this case, the null is true, which is that the probability of being left-handed, given that you're male, equals the probability of left-handed given that you're female. All right? So what this is saying, the null hypothesis, is that males and females have got the same proportion of left-handers. Or conversely, and the mathematics is dead easy, I won't go through it, it's a bit cumbersome, that a left-hander is just as likely to be male or female as a right-hander is. You can see it's 10 out of 40, and here it's 20 out of 80. I'm not interested in the fact that I've got 40 and 80. I'm not interested that I've got more right-handers than left-handers. That's just part of the population. I'm interested in the difference.
No, track 30.
That's 30. That's 30, and that's 90, isn't it? I'm interested in the difference between these two guys here. So really, that's what it looks like. But of course, if the null is true, 40, 80, 30, and 90. Here, the null is that the left-handers and right-handers are in the same proportion. It might look like this. That's gone down, so that's got to go up, and that's got to go down. Okay, that's still consistent with the null hypothesis, because it's just that, but plus random variability. How about this? What that tells me is that of the males, nearly every one, 97% or whatever it is, 90-something% anyway, are left-handed, and of the females, most of them are right-handed. See, this is not consistent with the this is not consistent with the null hypothesis of equal probabilities. Okay, this is my stock example, male and female, but this one works as well. There's one extra thing. Let me just show you how this works in practice. Let's do this one here, and I'll show you examples of this later on. We'll do this in the tutorial next week. I'm going to give you an example of how to analyze this statistically with using R. 6, 3, 7, 12. 6, 3, 7, 12. Oops. You'll see that when I put the numbers in, 6, 3, 7, 12, it reads it down in columns for reasons that are computer theoretical. 6, 3, 7, 12, yeah? And then I say 2, 2 to mean 2 rows and 2 columns. And if I wanted to be clever about it, I'd label the rows and the columns with my stuff and families and on the line and not, but I'm not going to do that. Rather than mucking around with d-hyper, you've got a thing called Fisher test. Yeah? And Fisher's exact test tests the null of independence of rows and columns, which is what we've talked about, in a continuity table with fixed marginals. The marginals are how many row and the totals of the row and sums. There's one subtlety, which is this. Alternative equals two-sided or one-sided. You'll remember that when I was talking about the Gaussian, I've got to wrap this up now. When I was talking about the Gaussian, we were talking about one-sided and two-sided tests. We were talking about either having just that as the critical region for rejection or two-sided. In this case, we were just looking for an increase. In this case, we were looking for an increase or a decrease. You'll remember that from 3 weeks ago, is it? Some time ago now. So this is a one-sided test and a two-sided test. What we see here is a one-sided situation because she said you've taken your stuff preferentially. She didn't say your stuff or my stuff preferentially. She didn't say, oh, you've left your stuff in the bag. She said you got yours out. So this is a one-sided test because I'm only interested in the number of underpants being more than you'd expect, not more or less than you'd expect. So it's a one-sided alternative, which I can do using this line here in Fisher's exact test. If I specify alternative, two-sided means different from, this means greater and this means less. So I can do that now with R, and then I'll finish here. And there's my p-value, 0.142, which is exactly what I got with the previous way of doing it. So this Fisher dot test, all that does is go through all this hypergeometric calculation with the observation, or one more extreme, depending upon more extreme being just on one side or further away from where you expect, and calculates the p-value in one fell swoop. Significant or not?
No.
Go and tell my wife. Yes?
Can you explain that greater alternative equals to greater? Does that mean, so do you want the p-value at 2.5% at each end?
Yeah.
5%?
It is, that's exactly what it is. It's at each end, either far more or far less than you expect. But I'm not interested in far less. She didn't say to me, oh, you're leaving your underpants in the wash. She said to me, you're getting your stuff out before everybody else, so it's just bigger than expected.
If you have both tails and p-value is, let's say 0.7, would that be significant or not? Do you want the cut always to be at 5% or
Yeah.
5% each?
No, it's always the total area is always 5%. I'll cover this in lectures next week. I'm covering one-sided and two-sided next week. Okay, I'll stop it there, and we'll cover lots of examples of this in the tutorial next week. Okay.